Hello everyone. Today we will see what are next generation sensors. Now, with the need of Industry 4.0 and the Internet of Things, the requirements for the next generation sensors have evolved significantly. The first need is the interoperability of the networks, transducers, and control systems of different manufacturers. That is, sensors need to work across diverse systems and the networks using standardized protocols in order to ensure seamless data flow between the devices, controllers, and the platforms in both the industrial and the cloud based systems. So, here the solution for this is uh, to ensure the interoperability, the sensors must support multiple communication standards such as Ethernet or IP and IoT protocols. And additionally, edge computing and cloud based platforms can help bridge gaps between the different systems, enabling the sensors to work together regardless of the manufacturer. Then, second is compatibility of the sensors with multiple sensor actuator bus standards, reducing the wiring cost and the complexity. That is, multiple communication standards. So, here the next generation sensors must be capable of working with multiple bus standards and like they have to support the plug and play compatibility. Then sensors can easily be added to the existing network without complex rewiring, and wireless sensors and low power wide area networks, that is LPWAN, can further reduce the need for extensive cabling. Okay, so here the compatibility with different sensors, actuators, bus standards help simplify network setups and maintenance, and the ability to reduce the wiring complexity. It is very important in the model like a modern scalable industrial environments. Then next is the analog to digital integration, where there is interconnection of the analog transducers with the digital networks. So here the integration of the analog to digital converters in the sensors along with the IoT gateways allows the analog signals to be converted and transmitted over the digital networks. So the sensors which are embedded with the sensors with the embedded IoT communication protocols help to bridge the gap between analog inputs and the digital platforms. So in some cases, edge computing devices can process analog data locally before sending it to the cloud and reducing the latency and bandwidth usage. Okay. Then you have next is leveraging existing infrastructure, that is increasing the use of existing networks instead of proposing new standards. Okay. So here that is, instead of building new communication standards, next generation sensors must enhance the existing protocols and the networks and ensure that cost effective and smooth transitions to be more advanced systems. So here these all are the need for the next generation system. First is the interoperability, then multiple communication standards, analog to digital integration, leveraging existing infrastructure. Okay. Then next you have features of smart sensors. So these next generation sensors, these are often called as smart sensors. Okay. And these are called so due to their integration with the processing power and the communication capabilities, and these sensors are designed to be more autonomous and capable of self diagnostic, then self calibration, and providing real time data directly to the cloud or centralized control systems. So first feature is the integration of the sensors and actuators with the processor and a communication module. Like unlike the traditional sensors which only capture the data and need to be connected to a separate processing unit or controller, the smart sensors, they have built-in processing power and the communication capabilities, and they are capable of not only measuring the physical quantities, that is temperature, pressure, humidity, but also they perform the initial data processing, analysis, and the communication. One example for this is the smart temperature sensor, which will measure the temperature, process it, and then it will directly send the data to the IoT platform or the cloud service without requiring an intermediary system. Then next is the IEEE 1451 standard. So here, according to this standard, a smart sensor, it is defined as a device with the ability to connect to a processor or a data network with a standardized physical connection. Okay, and here the standardization of these physical interfaces and communication protocols, it is very important for ensuring the interoperability between or across the different manufacturers and the technologies. Next is functionalities of the smart sensors. First is self-calibration. So here smart sensors, these can automatically calibrate themselves over time in order to maintain the accuracy and compensate for environmental factors such as temperature fluctuations or the component aging. Example here is the smart pressure sensor, which will adjust itself when it detects the drift in its readings over the time due to the temperature changes. Then second is the communication. So here communication with external systems for real-time data access. That is the smart sensors, these then communicate data and sometimes even control the signals to other devices in the network. Example is smart humidity sensors, which will send the real-time data about the air quality to the center, like a central HVAC control system, and it will enable the automated adjustments. Then third is computation to process data locally and reducing the dependency on the centralized systems. That is, these sensors, these will often have the processing power to perform initial computations on the sensor data before it is transmitted. So here example is a smart vibration sensor, which will perform the basic analysis to detect the anomalies like motor malfunctions, or it will only send the data if certain thresholds are exceeded. The next is multiple sensing or multi-sensing capabilities to combine multiple sensor types in one unit. Here some smart sensors, these can integrate multiple types of sensing capabilities into a single device, and they will make them more versatile. So example are multi-sensor, like it will measure the temperature, like simultaneously it will be measuring the temperature, then humidity and the pressure, and it will provide a comprehensive view of the environment in one unit. The next is the cost improvements over time by reducing wiring, devices and maintenance. So here smart sensors, these are designed to be more cost effective, and these will offer more value per unit. And example here is instead of deploying the separate sensors for the temperature, humidity and air quality, a smart environmental sensor will provide all the data which is needed in one device. Okay, instead of using separate devices for each and every parameter, we will use a single smart environmental sensor, so which can provide all the data needed in single, that is one device, and it will reduce both the upfront and the operational costs. Then next are the limitations of the smart sensors. So first is the predefined embedded functions. Customization not possible. It means that many smart sensors, these are designed with pre-programmed functionalities that are fixed at the time of manufacturing. These sensors cannot be easily customized to accommodate specific use cases or future changes in the system requirements. That is, once the sensors are programmed at the time of manufacturing, that cannot be easily changed according to the requirements. Okay, what are the limitations for this? It means that the sensor functionality is restrictive, and it prevents it from being adapted to new applications or evolving needs of an industry or the environment. Okay, like example is a temperature sensor with built-in calibration settings, which might not be able to adjust its calibration method if the system requires different conditions or different variables. Second is narrow application spectrum, like Smart sensors, these are designed to be more versatile than the traditional sensors, and they are often optimized for specific applications. And here the narrow range of functionalities means they are not like always suitable for broader or more diverse environments. Example is a smart sensor designed for industry. It might it will be used like it is not adaptable to the smart home applications. It is used only for the industrial purpose, okay, without significant redesign or the limitations of its functionalities. The next is sensor data aggregation not possible. It means that many smart sensors, these can collect data, but this cannot aggregate or cannot combine. They cannot combine the data from other sensors or the systems, and this will limit their ability to provide a holistic view of the monitored environment. Okay, so uh, this data aggregation, it is one of the limitations here. And next is external processor for sensor calibration. Here the smart sensors, these can perform basic processing, and they still require an external processor or system to carry out complex tasks like calibration, which can be time consuming and resource intensive. Okay, and last one is the basic communication protocols. So here many smart sensors, these will use legacy communication protocols which will not which are not fully compatible with the advanced or the future systems in industry 4.0 or the IoT environments. So here like one example is a smart temperature sensor in legacy manufacturing plant. It may use the uh, Modbus RTO, but integrating it into a cloud-based system for predictive analysis would require converting the data into a more modern protocol like MQTT. Now, in order to overcome these all limitations, the next evolution of the sensors is nothing but the intelligent sensors. Okay, like which take the smart sensors to the next level by offering more advanced functionalities than flexibility and the integration capabilities. These are some of the key features of the intelligent sensors. First one is these are capable of processing the sensed data and performing the predefined functions. Okay, these intelligent sensors, these not only collect the data but also process it and perform the predefined functions based on the data. So the second feature is these are capable of customizing the embedded algorithms on the fly, that is algorithm customization. Here intelligent sensors, these can dynamically adjust or update the algorithms embedded within the system, and this adaptability allows them to adjust to changes conditions changing in conditions without requiring external intervention. Then third is the capable of managing and controlling the external sensors or devices, that is the external device management. Here intelligent sensors, these are capable of managing and controlling other external devices or the sensors within a broader system, and this will allow for the coordinated actions and more complex multi sensor systems that can optimize the functioning of the entire system. And the last one is integrated components. So here it comprises of a sensor, microcontroller, memory unit, it may be a flash, RAM or ROM, and the platform for running the sensor application. These are some of the key features of the intelligent sensors. That is, first is the data processing and action, then algorithm customization, external device management, and integrated components. And these are some of the advantages of the intelligent sensors. First is the reduced data communication. That is, intelligent sensors, these can process data locally and reduce the need to send raw data to a central system or the cloud. And instead of transmitting large volumes of data, only relevant or processed information is shared. Second is the reduced power consumption. Here, by processing the data locally and managing tasks autonomously. The intelligent sensors, these often operate in low power modes and only activate the communication or processing when it is necessary. Okay, so by doing this, what happens? These intelligent sensors, these will conserve the energy and they will extend the battery life in the IoT devices. Next is the application specific customization. Here the intelligent sensors, these can be customized in order to meet the specific needs of an applications, such as adjusting their sensitivity, then algorithms and processing capabilities which are based on the environment or the task. Then next you have continuous calibration and monitoring sensors, where the intelligent sensors can self-monitor and calibrate continuously in order to ensure accurate and reliable performance even over the extended periods. Okay, and next is adaptive sampling rate and sleep-wake cycles. So here these sensors can adjust their sampling rate. Okay, that is how often they can collect the data based on the environment, and they can enter the sleep modes during the periods of inactivity in order to conserve the energy. Okay, and by doing so, they will balance the responsiveness with power efficiency. Then next you have shorter software development time. So here these sensors are often programmable and these come with the pre-built software libraries and making the development process faster and easier. Okay, and the last one is improved compatibility of the sensors. So here these sensors, these are often designed with interoperability in mind, meaning that they can easily integrate with other devices or the platform, and whether they are in the same ecosystem or from the different manufacturers. So these are the advantages of the intelligent sensors. Now these are the smart sensors and the block diagrams of the smart sensors and the intelligent sensors. Okay, so here you can see a smart sensor, it can integrate essential signal processing and embedded features, but it relies on the external application processor for advanced computations. And the key components here are the digital interface, you have embedded features, then signal conditioning, A to D, that is analog to digital converter, and sensor or MEMS. So here digital interface, it will connect the sensor to an external application processor. Embedded features are like these may include the calibration, then compensation and the self-diagnostic. Then signal conditioning. Here it is processing the raw analog signal from the sensor. Okay, like example is they will be using amplification or the filtering techniques here. And this A to D, it will convert the analog signal to the digital signal. Then sensor or MEMS, here this is the core sensing element. It may be accelerometer, gyroscope or the temperature sensor. So here the characteristics of the smart sensor are this can process basic sensor data before transmitting it, and these will improve the accuracy through built-in calibration, and it requires external processor for decision making. Whereas intelligent sensors here, it is an advanced version of a smart sensor which include its own processing and memory capabilities. Okay, so here the key components are the digital interface. Then you have microcontroller unit, MCU. Okay, this one, which comprises of the RAM, ROM, microcontroller and the flash memory. So here RAM, it is temporary memory for the active computations. ROM, it stores firmware and predefined instructions, and the flash memory, it will allow firmware updates and the long-term data storage. And it also has the A to D converter and sensor or the MEMS. Here these can perform the local decision making without external processing, and these can store the historical data, and these can support the firmware updates and also support multiple sensors, making it more versatile. And these can integrate the artificial intelligence or the machine learning algorithms for advanced analytics. So this is the difference between the smart sensors and the intelligent sensors. This is some of the comparison of the smart sensor and the intelligent sensors. So these are the features which are considered for comparison. Here the processing power is limited in smart sensors, whereas it is higher in the intelligent sensor. And the data storage is minimal, and here these uses RAM, ROM, flash storage, and it requires an external processor. Here it can process the data independently, and it will not support multiple sensor, whereas it supports the external sensors. Then here the real-time decision making is limited, and here it is possible that it can make more real-time decisions. And the basic sensing it is used for complex applications, whereas it can use AI or ML predictive analysis for complex applications. These are some of the comparisons or the differences. Then next you have applications of next generation sensor. The first uh, application is smart manufacturing, where real-time monitoring and automation of the production lines is carried out. Second is wearable technology. Here you will be having sensors which are embedded in the textiles for health monitoring and the performance tracking. Then you have automotive safety, that is advanced driving systems which use sensors for autonomous driving features. And you have fault detection, that is predictive maintenance, fault detection and forecast using the machine intelligence. That is sensors use machine intelligence for fault detection and the forecasting. Then you have biomedical devices, that is the non-invasive biomedical devices, where the sensors in the biomedical field are increasingly used for non-invasive monitoring of vital signals, vital signs and the health parameters. So these systems, sensors, these will enable real-time tracking of the blood glucose level, oxygen, then heart activity without the need for needles or other intrusive methods. That is nothing but the non-invasive sensors. Then you have environmental monitoring. So here chemical sensors are used for analyzing the environmental conditions, and these will ensure the safety. That is chemical sensors, these can analyze and detect composition of the substance or materials and identify specific chemical properties or the concentrations. Then you have design challenges in the next generation sensors. So here there are hardware issues and the software issues. Regarding the hardware issues, the first is the limited power, where there is a need for energy efficient designs using the low power electronics. Then energy harvesting. Energy harvesting can be done by solar vibration or the thermal, and the sleep wake mechanisms. Then you have high response time, that is delays will affect the real time applications. So here high speed processors, edge computing, and AI driven predictive analysis for rapid decision making can be used. Then you have synchronization, which is essential for the data fusion. So for this you can use high precision time protocols, then clock synchronization mechanisms, and the edge computing. The next hardware issue is limited bandwidth. That is here like massive sensor networks, these can generate large data streams that are needed to be transmitted over wired or wireless communication channels. So here the bandwidth limitation, it will lead to the data loss, then latency or congestion, which will impact the performance, that is impact the performance of the system. So here data compression, prioritization techniques, and adaptive bandwidth allocation can be used in order to optimize the network traffic. Then you have security issues which are vulnerable to the cyber threats, and these require encryption and the secure protocols. Okay, and the software issues are software partitioning, that is like in industrial IoT, it relies on the efficient task distribution across the edge, then gateway and the cloud computing layers. And here the challenge is that there is improper partitioning, which leads to the increased latency or the redundant computations, which will affect the real-time automation and decision making. So for to overcome this, edge computing is used, which will handle the real-time data processing, and gateway layer is also used, where it acts as a filtering and the aggregation point, which will reduce the unnecessary data transmission. And cloud computing is used for optimal performance, which will store and process the historical data for long-term analytics. Okay, and machine learning and enterprise level decision making is also used. So these are the design challenges in the next generation sensors. Thank you.